Welcome in our mathematics class, where today, as we continue with algebraic techniques 2 and indices, we are going to look at the zero index and the power of power. The zero index and the power of power. Previously in the lesson, we saw that we have got the behavior of powers when we are adding and when we are multiplying and when we are dividing. That's when we looked at the law of index, when we look at the multiplication and division. So currently, we want to look at the behavior of this zero index. How does it behave and how is it treated? I want you to consider when we expand a number like 5 raised to the power of 3 into bracket 4, then we know that this is the same as having what is inside the bracket 4 times. So this will be the same as 5 raised to the power of 3 times 5 raised to the power of 3 times 4 raised to the power of 3 times 5 raised to the power of 3, 4 times. At the end of the day, when you look at the law of multiplication of indices, if the base is the same, then we shall add the powers. So this one will give us, when you add, it gives us 12. So this is equivalent to 5 to the power of 12. However, you would have just taken a shorter method by looking at this. When you have a power of power, you'll simply multiply the powers. That is 5 raised to power 3. Power 4 is simply multiply the powers. That is what we get when you are putting a power raised to another power. Similarly, it can be observed when you have 6 raised to 4 into bracket 2. This one is the same as 6 raised to 4 times 6 raised to 4. So this one, if you can see, the base is the same, so we add the powers. We'll find that this is 6 raised to the power of 8. Alternatively, we would have 6 raised to power 4 times 2. The power 2 again, this would be 6 raised to 4 times 2, which is 6 raised to 8. That is the behavior of power power. So we can conclude here. We can conclude here by saying this. We can say that if we have a number like a raised to m in bracket n, then the rule here tells us this one will be equivalent to a raised to mn. And that is how we shall apply this rule all through. For 0, here is a bit different. We say this. When a number is raised to 0 to the power of 0, when a number, let's take note of that, when a number other than 0 itself is raised to the power of 0, the result is 1. Any number except what? Except 0. That is a rule. You must observe it. We shall always use it, and it's a fact. In other words, what we are trying to say is this. 2 raised to 0 is 1. 3 raised to 0 is 1. 4 raised to 0 is 1. 2 raised to 1 is 2. 3 raised to 1 is 3. And 4 raised to 1 is 4. A number raised to 1 is a number. A number raised to 0 is 0. Is 1. A number raised to 1 is a number, but a number raised to 0 is 1. We must observe that. So precisely what should we be able to recall here? When a number other than 0 is raised to the power of 0, then the result is always 1. We should be able to observe that and maintain that. And when we have a power raised to another power, then the rule says that if we have m raised to another power, the answer should be the product of those powers, which is a power m and n. We also need to know that the expressions involving powers can be expanded. Let us see here. Now, this is what we have. 3 times 5, and then close the bracket, we have 4 outside the bracket. This one can also be expanded, and if you expand it just the way we saw earlier on while we were expanding algebraic expressions, then this one will be 3 raised to the power of 4 multiplied by 5 raised to the power of 4. That is 3 raised to the power of 4 multiplied by 5 raised to the power of 4. And if we had 2 times 5 raised to the power of 10, this one would give us 2 power 10 times 5 power 10. That is how the expression involving powers can be expanded. So let us look at workable exercises and see how to approach and apply what we've gone through. Let us start with the first one. 4 raised to 0 multiplied by 8. The rule, we are supposed to solve using the index law. The index law tells us a number raised to 0 is 1. Therefore, 4 raised to 0 times 8 is the same as 1 multiplied by 8, which is equals to 8. That is what we shall get. But for the second part, 4 raised to 0 is 1, times 8 raised to 0, which is 1. 1 times 1 you will get is 1. So the results here is 1, and the results here is 8. Simplify the following expression using index laws. And the first one is 2 to the power of 3 in bracket the power of 5. And B, we have 5 to the power of 2 in bracket the power of 4 multiplied by 5 to the power of 3 in bracket the power of 2. So starting with the first one, 2, 3 raised to 5. The law says AM in bracket n is the same as AMN. Therefore, if we have 2 raised to 3 in bracket 5, this one will be the same as 2 into 3 times 5, which will give us 2 raised to 15. It will give us 2 raised to the power of 15 because of this law here. For the second one, We have to apply the rule of power first, and then we come ahead and apply the rule of the same base. So here, as we have seen, a power m power n is the same as a m n. So we can simply look at this and simplify it. And here you'll find that 5 power 2 power 4 is 5, 2 times 4 as the powers, multiplied by 5, 3 times 2 as also other powers. This one will give us 5 raised to the power of 8, multiplied by 5 raised to the power of 6. Because the base here is the same again, when the base is the same, we move ahead and have it 5 raised to 8 plus. Take note, this is addition unlike the other one, plus 6. Why? Because what we have here, we are multiplying numbers with the same basis. So this one will give us 5 raised to the power of 14. Let us see how to simplify expressions with non-numerical basis, where we have either letters or unknown or pronumerals represented and having the powers. So this one is a situation where we have letters and we need to apply the law of index here. Simplify using laws. Using index laws. That is what we have, x power 2 into the power of 4 over x power 3 times x power 7 over x power 2 into the power of 4. We handle each part independently. The first one is the same as x power 2, and then power 4 is 2 times 4, which is 8 over x power 3 multiplied by x power 7 over x power 2 times 2, which is 4. Interestingly enough, from one term here of this numerator and denominator, and also this side, the bases are the same. So these powers can be worked on. You'll find that when I deal with this one alone, it will become x power 8 minus 3. X power 8 minus 3. So this is x to the power of 8 minus 3. So I'm done with this part. Multiplying by this part is x to the power of 7 minus 4. X to the power of 7 minus 4. This one here, now I conclude this part. Now I can go ahead and find and simplify. This is x power 5 multiplied by x power 3. Because the base is the same, we shall add the powers and we shall have our answer as x to the power of 5 plus 3 which is 8. So it's not only on numerical values, but also on numerical values, the index law will always work. It will always work. Having said that, we can conclude that particular part by saying that when you are working with indices, it is very important that the law are observed. You cannot work or operate or solve indices without observing the laws of indices. And that's why we are able to work with both numerical and non-numerical indices. Now, let us now change over and come to a new topic that we shall review what we've been going through. And this topic is called Equation 2. And here, we are going to look at the number and algebra. And when you talk of equation, it's not the first time you are coming across this. It is not a new thing. So let us start by reviewing equations. Reviewing equations. What exactly are we trying to say here? We want to refer to what we already know and bring in what we don't know. As we saw earlier on, an equation is a statement. That's what we know. An equation is a statement that two things are equal. That's why we are calling it equation. We can have, for example, if we have 2 plus 2 is equals to 4. This is an equation. It is very true that the left-hand side is 4, because 2 plus 2 is 4, and the right-hand side we also have 4. This is also a true equation because it means that on the left-hand side, 7 times 5 is 35. On the right-hand side, 30 plus 5 is also 35. And we can also agree and now say that when we have equations, even if we have unknowns or pronumerals, when they are equated means when we solve, they should give us values that will equate the two. So also, 4 plus x is equals to 5 plus y is also an equation, depending on how we shall solve those. And if we have equations if we have, for example, an equation like this, this is an equation. But the moment we reduce it until we find the value of x, then it will mean what we are doing is solving. So to solve an equation simply means that we are reducing an equation. We are reducing an equation until we find the value of the unknown. For example, this particular case, we would subtract 3 this side, minus 3 that side. We remain with x is equals to 7 minus 3, which is 4. So this 4 is a solution of the equation. It gives simply the value. When you substitute here, the left-hand side will be equal to the right-hand side. So what are we supposed to know about equations? First, we need to understand that an equation is simply a mathematical statement that tells us that two expressions are equal. It's a mathematical statement that tells us that two expressions are equal, where the expressions could be 4 plus x is equals to 32. This one is a mathematical statement. It is equated, and therefore this is an equation. However, some equations are false. Some equations are true. For this one, we don't know what the value of x will be to give us the correct statement. For example, it is true that 4 plus 28 is equal to 32. That one is okay. However, it is not true. Because if someone had said 4 plus 29 is equals to 32, this one would be false. So that's why we are saying sometimes some equations may be true, others may not be true. In the equation again, we need to know that we have pronumerals in the equation, and these pronumerals in the equation, sometimes a pronumeral in an equation will be called a known. It will be called a known. We do not know it until we solve it. And when we have a false statement like the one I had just given earlier on, that 4 plus 29 is equals to 32. It was a false statement. So we want to say that false statements sometimes can be made true. If you are told, you'll be put this sign there, that 4 plus 29 is not equal to 32. Is it true or is not true? That's a fact. It is true. So this is a false statement that has been changed to be true by putting the sign which shows is not equals to. When we talk about an equation, always all the equations must have the left-hand side and the right-hand side. They should be always there. The left-hand side and the right-hand side must be within on the equation. And as we have seen, what we are calling a solution, what we are calling a solution of an equation, this is the value that makes the equation to be true. It is the value that makes the equation true. A solution is what the value that will make the equation true. If we were to solve 4 plus x is equals to 32, and then we minus 4 here, you'll find that this will give us x is equals to 28. This 28 is a solution. The 28 is a solution. If this 28 is a solution, then the process of getting this solution is called solving. So while you are solving the equation, you are simply looking for the value of, simply looking for the value of x, or the value of the unknown. That is called solving. Also, sometimes some equation could have no solutions at all. Others could only have one solution, and sometimes we have more solutions. So as we go by looking at the question, we should be ready to come across these points that we have come across. Let us look at this question. For each of the following equations, state whether they are true or false. For each of the following equations, state whether they are true or false. And if they are true, we shall say they are true. If it's false, we write false. First one is 3 plus 8 is equals to 15 minus 4. Second one, 7 times 3 is equals to 20 plus 5. And lastly, x plus 20 is equals to 3 times x, given that x is equals to 10. Let us look at the first one. Because these are all numerals, we can just work out 3 plus 8 gives us what? 11. And 15 minus 4 will give us. So we can say this statement is true. For the second one here, 7 times 3 is 21. 20 plus 5 gives us 25. Is 21 equals to 25? Definitely it's not. And if it's not, this statement is what? False. And lastly, given that we have x plus 20 is equals to x times is equals to 3 times x. But x is 10, so we substitute. We substitute where x is. So x is 10, this will be 10 plus 20 is equals to 3 times 10. This is 30 is equals to 30. So we can agree and say that this statement is true. So that is how to identify whether when a statement is true or is false. Now, let us look at a question on where we are going to see if we can state a solution to an equation. Are we able to state a solution to an equation? State the solution to each of the following equations. State the solution to each of the following equations. Solutions to this, and we need to work out and find the solution to 4 plus x is equals to 25, 5y is equals to 45, 26 equals to 3z plus 5. Now, because we've been asked to state, and we have the knowledge of approaching this, so for this one here, what could be the solution? If we were to work out by solving, we would still get it, but you can still do it offhand. So for the first one here, if you minus 4 here and minus 4 here, you'll find that x is equals to 21. So what we are looking for there is simply 21. X is the solution and x is 21. For this one, having reached here, we shall divide here by 5 and divide here by 5, so that 5y divided by 5 is y, and 45 divided by 5 is what? Is 9. So 9 is the solution to that equation. And the last one here, we have on the right side 3z plus 5, and this side 26. So we minus 5 here and minus 5 this side. You'll get this is 21 is equals to 3z. And then you divide by 3, divide by 3, you'll get this one is 7 is equals to z, which implies that z is equals to 7. That is our solution. So all through here, we have been able to state the solution for the first one is 21, the second one is 9, and the last one is 7. So even if we had this set on the right-hand side, it doesn't change anything. It does not change. It just remains that it will give us the solution the way we want. Only interchanged here, sometimes it is easier to work out when you interchange the left-hand side and the right-hand side. But for this case, it was still not affecting much. So let us now look at what we call equivalent equations. Equivalent equations. And here we want to look at what exactly do we understand when we say equivalent. Mostly we get equivalent when we have the right-hand side and the right-hand side and the left-hand side are being equal. So we have an equation, we can obtain equivalent equation by performing some operations, both like what we've been doing initially, perform some operation whereby whatever happens on the right also happens on the left. We'll always find that what you are having is equivalent. For example, if we have an equation like 2x plus 4 is equals to 20. This one already is trying to tell us that what we have on the right is the same as what we have on the left. But for us to solve for x, we must use equivalent equations at any given time. So here, what will happen on this side should happen here. So we want to get the solution and arrive to the value of x. So when we subtract 4 here, we should also subtract 4 here because of equivalent idea. So this one will remain 2x is equals to 16. When you divide by 2 so that you remain with x, then you'll also divide by 2 here, you remain with 8. So you find that ax is equals to 8. When you take this 8 and replace here, is it going to give us exactly the same so that the statement can be true? 8 times 2 is 16 plus 4 is 20. So this is a true solution for this, and therefore we have approached this solution by looking at equivalent equations. So it is necessary to know the following. We can say that two equations are equivalent. Two equations are equivalent if you can get from one to the other by repeatedly doing the following. Two equations can be said to be equivalent if you can get from one to the other by repeatedly doing the following. And what do we do? First here, adding a number to both sides. If you happen to add the number to both sides, then you'll be in the process of obtaining an equivalent equation. Then we also find that 2, if you are subtracting a number from both sides, again, you will be in the process of attaining an equivalent fraction, an equivalent equation. If you are subtracting a number from both sides, you'll be doing the same. You can also get or arrive at equivalent equation if you're multiplying both sides by a number other than 0. Not a 0, any other number but not a 0. Dividing both sides by a number other than 0. Again, that one you will be working out to have equivalent equations. You can also get equivalent equations if you do this other last statement. You can get equivalent equation if you are swapping the left-hand side and the right-hand side of the equation. If you are swapping, then you will be actually having equivalent equations. So this point needs to be observed anytime you are dealing with equivalent equations. So to solve an equation systematically, you should repeatedly find equivalent equation, and when you find the equivalent equation, then it will be much more simpler to work on it. So you're saying for you to solve an equation systematically, you must find equivalent equation. Look at this. This is an equation. 5x plus 2 is equals to 32. We need to solve this systematically, and we shall all the time be writing equivalent equations until we arrive at the answer. So the very first thing here to do is to subtract 2 on both sides. When you subtract 2 both sides, this is 5x plus 2 minus 2, you remain with 5x is equals to 32 minus 2 is 30. After this, as we say, dividing by a number other than 0, the number to divide by here is 5, so divide by 5, divide by 5. 5x divided by 5, you will get x. 30 divided by 5, you will get 6. You can't move any further, but the x is 6. Therefore, the solution of this equation is x is equals to 6. It is always advisable to check a solution by simply substituting the unknown in the left-hand side so that you can confirm if it is equals to the right-hand side. I've said it is always necessary for you to confirm your answer. to check your answer by substituting your answer to the left-hand side and confirming if it is equal to the right-hand side. So this question is asking us to show the results of applying the given operation to both sides of this equation. And here we have a first equation as 8 is equals to 40. In bracket they have told us divide both sides by what? By 8. So if you choose to divide both sides by 8, 8y divided by 8 is y, and 40 divided by 8 will give us 5. So you see, it has moved us a step. We have the solution of y is equals to 5. The other one we have is we have been asked to minus 10 from both sides of the equation 10 plus 2x is equals to 36. 10 plus 2x is equal to 36. Then we have been asked to subtract 10 from both sides. So we shall subtract 10 from this side, also subtract 10 from that side. 10 plus 2x minus 10 will remain with 2x is equals to 36 minus 10 will remain with 26. You will remain with 26. So this is where we shall stop. We have not been asked to solve. We have only been asked, is it possible for us to apply the rule of equivalent equations on both sides and see it working? And that's what we are doing here. For the last question, they have given us 5a plus 3 is equals to 12. In bracket, we are supposed 5a minus 3 in bracket, 5a minus 3 is equals to 12. In bracket, add 3 to both sides. So if we are to solve this, we shall add 3 here and add 3 here. 5a minus 3 plus 3, we shall remain with 5a. And 12 plus 3 will give us 15. So we can simply say we are able to add 3 on both sides until we arrive at equation 5a is equals to 15. 5a is equals to 15. This is about equivalent equations. Let us now look at solving these equations systematically. Solving equations systematically. Solving equations systematically. Let us look at that and see what we shall get. Looking at these equations, the 3 of them, we want to solve them systematically. And for us to go and solve them systematically, we shall observe all the rules of solving the equations. X minus 4 plus 16. The first step we need is to see what are we supposed to do. Add 4 here so that we get x minus 4 plus 4 will give us what? It will give us x. And then 16 plus 4, it will give us 20. So already here, 20 is our solution. So we can say the solution for this equation is 20. But we have been asked also to check our answer. Is it true that 20 is the right answer? So if we substitute here, it will be 20 minus 4 is equals to 16, which is very true because 20 minus 4 is 16. For question 2, we have 2u plus 7 is equals to 17. So here, when you look at this, what exactly are we supposed to start with? You'll realize that we need to work out the constant this side, that is 7. So we shall subtract 7 here. It has to happen on both sides because of being equivalent equations. So this one will be 2u plus 7 minus 7. We remain with 2u is equals to 7 minus 7, which is 10. Then the next step, you divide here by 2 so that you remain with u. And the other side, you divide by 2 so that you remain with 5. So our solution is telling us that the value of u in this equation is 5. Can we check our answer by comparing the left-hand side and the right-hand side if it gives us the right information? So from here, we have 2u plus 7 is equals to 17. So, and u is what? Is 5. So 2 multiplied by 5, 17. 2 times 5 is 10. 10 plus 7 is 17. So 17 is equals to 17. That is very true. So it's the correct statement. Lastly, we have 40 minus 3x is equals to 22. From here, what do we need to work out first? The constant is there. The unknown is with x. We need to find this x. So the first step here, we shall subtract 40 here. We have done integers, both positive and negative, so we should not have a problem on working out this. 40 minus 40 minus 3x will give us minus 3x. 20 minus 40 is minus 20 or negative 20. Remember, our interest is to find the solution for x and not anything else. So we shall be required to divide this side by negative 3. And also the other side by negative 3. In our previous lessons about dividing negative integers, we said if we are dividing integers that have like sides, or both of them negative or both of them positive, they should give us a solution that is positive. So minus 3x divided by 3 will give us positive x. Then minus 20 on the other side divided by minus 3 will give us a positive of 3. It will give us a positive of 20 over 3. Now, looking at this, so let us make some correction here. It's supposed to be 22 and not 20. So we have 40 minus 3x equals to 22 and not 20. So the first step was to subtract 40 both sides. And when you do that, you'll find that this one remains minus 3x. And the other side, we shall have minus 18. Then we have minus 3x, but the solution we are looking for is the value of x. So we divide here by minus 3 on the left, and on the right again we divide by minus 3. So minus 3x divided by minus 3 is x, and minus 18 divided by minus 3 will give us positive 6. So you find that the value of x here is positive 6. Let us go and confirm if at all is going to give us the right substitution. 40 minus 3x plus 22, if we substitute it is 40 minus 3 into x, and x is 6, is equals to 22. This one gives us 40 minus 18 is equals to 22, which is true that 22 is equals to 22. 22 is equals to 22. So that is it for today about equivalent equations and solving these particular equations. In our next class, we shall now go on and look at equations with fractions. Thank you.